Hello folks, welcome to the channel and welcome to this video. I am Saptarshi Mukherjee. I am a software engineer at Google and I am a competitive programmer. So in this video, I'll be discussing the problems D and D of this Codeforces round 930. In the last video, I had discussed in a good amount of detail the problems A to C. And in this video, I'll be focusing on problems D to E. What we saw in A to C was that we used some real good observation techniques. D and D I had absolved after the contest, and that was one of the reasons. This problem E was one of the reasons that took me this long to finally make the video. You can see that after the contest and after so much time only, there are 109 submissions for E. So yes, there are a good deal of things to discuss over here. But apart from optimization techniques, another good thing in D&D is that there has been also a use of classical algorithms over here. So here you will find a blend of some classical algorithms or classical techniques and some real good observations. So let's get started with problem D. Problem D tells you that it's a one-dimensional grid or a one-dimensional row of n elements, and each element is basically either a left arrow or a right arrow. Left arrow basically means that if there is a pinball which came to this cell having a left arrow, the pinball moves one cell to the left in the next second, and if it is the opposite, if we have a greater than if we have a right arrow over there, then it will move one cell to the right. That is the behavior of the pinball based on the character, based on that sign on that cell. Not only that, when the pinball has moved, that character will be inverted. So the movement of the pinball is driven by these arrows, but also according to the movement of the pinball, if the pinball is visiting one cell and then leaving that cell, regardless of the direction of movement and direction of getting bound left or right, whatever, the sign will change. So through an example, let's understand this. But first of all, what is the question? The question is n independent queries. Ith query, a pinball will be placed on the ith cell. So in the ith query, a pinball is placed on the ith cell. Placed means at that point, if it is left arrow, it will start moving towards left. If it is right arrow, it will start moving towards right. For each query, we have to say how many seconds it takes the pinball to leave the grid. Leave the grid, that is leave either the left boundary or the right boundary. So let us understand through this example. Let's say right, left, left. Let's say we have right, left, left. So if we start from here, we can say, okay, first second, we will move from this position to this position, and this one will get inverted, so it will become less than. Both of these remain less than. Next step, less than, greater than, less than, and it moves over here. Why am I moving to the right? Because I'm sorry. Okay, so at this point, this is left arrow. Left arrow means next step will be towards the left. So let us see. It is now this one gets inverted because it's moving away from there. So this is moving to the left, and this one remains as it is. What happened from the first step to the second step? It moved to the right because this was pointing to the right, and as a result, this changed to left. Next, this is pointing to left, so this one moved to the left, and this has changed opposite to the opposite, that is right. So this is the behavior. Next, this is left, so now it will move out of the grid. It will move out of the grid. So how many movements? 1, 2, 3. That is a movement, and when it moves out of the grid, you have to keep in mind that this will become right, right, left. Though it doesn't matter what it becomes, but still. So this is 3 steps. The answer should be 3. Let us see. Yes, the answer is 3. This is only the first answer. That is for the first, if the thing is placed on the first index, then this is the behavior. Then the answer is 3. What if the what if the thing is placed in between? The pinball is placed at the middle index. Let us see. Same thing, but now we are starting at the middle. So it will move to the left based on that arrow. So it moves here, right, left, and this one gets reverted, so this one becomes left. Sorry, it was left, so it becomes right. Yeah. Next, it moves to the right, so it will move here. It moves over here, and then this basically remains this. That one gets changed. Next, it moves to the right, so it becomes left, left, left. Now the pointer is over here. Next, it moves to the left, so we will have something like this. It will come over here, and we will have left, left, and that one gets inverted, this thing. Then once again, one more left, and both of them will be right. So basically from this one, it moves over here. Yeah. And the next step, it moves out of the grid, and we have right, right, right. So how many total steps? 1, 2, 3, 3, 4, 5, 6. Total 6 steps. That's sufficient for the time being. In 6 steps, from the middle position it will be out. So a quick analysis of time complexity. There are 10 to the power 5, 5 in 10 to the power 5, 50, sorry, zero point 0.5 million, zero point 0.5 million, you know, values over there. Is it 0.5 million? No, it's 50,000, right? Okay, no, 0.5 million. Yeah. So that many characters are there. Now the question is, for each, if I do a brute force thing, for each, if I do this simulation, left, right, for each of them, if it takes around big O n time, let's say it takes big O n time, then for each of the n characters, since I have to do, it will not fall in within time limit. N squared is definitely going to be above the time limit we have. The time limit is 2 seconds, so yeah. So now, what can we observe over here? One thing that I can observe directly is that when they were all right, it happened very smoothly. It just came to the left in this way. So ultimately, we had some complex thing over here, but ultimately it sort of concluded in this kind of a pattern. All are pointing in the same direction. This is one kind of observation. What is another kind of observation? That okay, this guy changed its route for the first time. Changed its route for the first time. Next time, did it ever change its route? Let us see. When it came to this guy and then it left, we see that it is pointing in this direction. This direction basically means the next time when it will come from the right, let's say it's come to the left, it will go out directly. What did I mention over here? First time, it was facing that side, it was right. Right means whatever comes from the right will be blocked. But then what happens? So when that gets blocked and then gets rebounded, when that goes away, this right gets inverted to left. And left means now the next time when that guy will come once again, that will come and that will go through. This is not going to block. This is going to become like this. And what happens if it again comes back from the left? Can I say, if it again comes back, by chance if it comes back from the left, can I say now it is favoring the direction? Now this is allowing it to go in that direction in which it is going. If it comes from the left, it will continue going in that direction. So if I take it differently, the other way of the picture as well, let's say I have a left arrow over here and something is going to it from the left. First time it gets rebounded, it will hit, it will come back. And what happens to this? This one changes itself to a right arrow. Next time what happens? If this guy from here, if it again comes back here, now this will get easy entry, it will go over there. It will go and this sign will change once again to left. If it comes back once again, it will again go freely. This will not become an obstacle, and this will again turn to the right. Now if it again comes back from the left, again it will have a free passage, which means that it will become an obstacle only once. That is an observation that for a given starting position, any I can become an obstacle at most once. Does it make sense? So now let us do this for a bigger example and see how it turns out. By the way, if it was never an obstacle, let's say it was not an obstacle for the first time, will it become an obstacle later? Let us see. So I'm starting over here, let's say towards my left. I have a pointer going towards my left. And over here, I have something to my right and maybe something over here. Now, when I cross it for the first time, it is not an obstacle, I'll just go through. What happens to this guy? This guy gets inverted, it becomes right. This guy becomes a right pointer, right arrow. Now when it will come back from here after getting rebounded at that, can I say it will have a free passage to the right? Either it leaves the grid from there or it will come back once again. When it comes back, can I say it has again got inverted to the left? To the left. So if it comes back and then hits this one, this particular thing, that one gets inverted, it will come back, and when it comes back, can I say again this guy has turned to the right because of this collision, because of this movement. So can I say if an I was not initially a blocker, was not initially a blocker, then it will never become a blocker. It will never, I'll highlight this, never become a blocker. So this tells me that okay, for every index, for any given index starting position, the right arrows to the left and the left arrows to the right are the only hindrances, correct or not? If I'm starting from this position, whatever right arrows are to the left and whatever left arrows are to the right, they are the only hindrances at only once. This will become an hindrance only once. This will become an hindrance only once. Only once, only once, only once. So how will the movement look like? If it starts towards the left, it basically goes there, comes back, goes there, up to there, comes back, and then again gets rebounded, goes there and leaves the grid. This is how it will look like. If it starts towards the left, what determines whether it starts towards the left? This particular symbol, whatever is present over here. If it turns towards the right, let's say it was pointing towards the right, then first time it goes there, next time it goes here, next time it will go up to that right point, then it will come up to the leftmost point, next it goes up to the rightmost point, next it comes and exits from the left boundary. In this case, both the exits are taken. In both the cases, exits are taken from the left or right from the left boundary. But anyway, you will have only one case. Either this will point towards left or this will point towards right. Only the initial direction matters. So one thing is clear. These indices matter to me. And based on this, it is possible to do a quick calculation. Okay, how exactly, I mean, you can just measure these segments. You can just add up these segments and you will see the calculation matches. Number of steps from here to here plus number of steps from here to here and so on. If you keep on adding, you will get the correct value. You can try this on this given examples. That will be a good exercise. Please do this. This will be a good exercise before you proceed to the solution idea or actual solution. Okay, now that you have understood these two very important points, that an opposite sign in the direction of movement becomes an obstacle only once. Opposite sign, that is initially opposite sign, will become an obstacle only once or at most once. And if it was not initially a blocker, it will never become a blocker. Now here, the reason I could not do it during the contest was that I thought in a certain, I would say classical way or a common way, that okay, if I have the answer, I thought it in this way. Up to here it was sort of clear to me. But then how to calculate it in the last 10 minutes, this was the way I thought. That okay, if I know the answer of I minus 1, can I find the answer of I? From here, can I find out this answer? So in some cases, it seemed like it is quite close. In some those cases where maybe both have the same signs or similar. In those cases, it was slightly close, but overall, it basically turned out that in most of the cases, it was quite difficult. So this was actually the wrong strategy I had, taken, because this has many cases. One case is both are right. One case is right left. This is another case is left right. Another case is left left. So you have so many cases. Now the thing is, some case may have an easy solution, may have an easy deduction. That okay, from here this can be easily reduced. But for most of the cases, what I saw is there are many things to be considered, which is not making this a really interesting calculation. And again, the confusion. From that, the confusion arose, okay, should I proceed from the left or from the right or together using some two-pointer kind of approach? This sort of killed my 10 or 12 minutes, whatever I had, which I could have utilized differently and probably solved the problem. But this was the wrong strategy that I had taken. Sometimes this strategy might help you, that based on one answer, you can find the next answer, etc., because there is a very close mathematical relationship. But over here, before going into that, what I did was basically, for one, maybe the answer was 4 plus 8 plus 3 plus 4, something like that, based on the distances, etc. And for the next one, it was maybe minus 1 on two cases and so on. So I tried to find out a relationship. But the right step in this kind of problems, the right step in this kind of problems is always to go mathematically and see that for this kind of situation, how is the mathematics working out? So let us take this example and see exactly how should the mathematics look like. Let us say we are working towards the left. Whatever right arrows are there, let me mark them as something like R1, R2, and the left arrows maybe mark them as L1, L2, L3. So if I'm moving towards the left, let me take another one, R3. What do I see? The first movement is from here to here, that is from this position, let's call it as P. From the starting position, let's call it as P. We are moving from P to R1, and that basically we can call it as these many moves, P minus R1. Next, I'll move from R1 to L1, which will basically look like L1 minus R1. I have named this because these are left pointed arrows and these are right pointed arrows, so I've named this as R. These are the right pointed arrows before P, those are left pointed arrows after P, and P is pointing to the left. So first I'll move from P to R1, then R1 to L1, then L1 to, as we discussed, R1 is no longer a blocker, it will freely pass through, so from L1 it will come to R2, so it becomes L1 minus R2, right? L1 minus R2, that is the distance. Then it goes from R2 to L2, L1 is no longer a blocker, so R2 to L2 leaves L2 minus R2. If I complete this, it will look like L2 to R3, and that means it will be L2 minus R3, and then R3 to L3, R3 to L3, and that makes it L3 minus R3, and then I can say, okay, from L3 to left. I mean, it will now go entire way to the left because there is nothing else to the left. So that means L3, you can say, considering that these are 0 indexed, we can say plus 1. So considering that these are all 0 indexed, all are 0 indexed, we can say L3 plus 1. Okay, cool. Now the question is, the summation of this is my answer. What do I observe? We have P at the beginning, we have plus 1 at the end, and rest of them, can you see they occur in pairs? Minus 2R1 plus 2L1, minus 2R2 plus 2L2, minus 2R3 plus 2L3. And this is also a very common thing you will see in these problems. You have to patiently write down the expressions and then the answer will eventually come out. So what we see is that we start from a certain position P, we are moving to the left, so higher the P, it matters in the positive way. So P, and then all the R's go in the negative way, so minus 2 into summation of Ri's plus summation of Li's plus 1. And now this gives us some cases that okay, if there were some extra R's over here, the calculation would continue. If there were some extra L's over here, then nothing would change because this has got rebounded, it would leave from there. If there are extra L's, that doesn't change, which means if we say okay, there are X number of right pointers at the left, and if there are Y left pointers at the right, and if X is less than equal to Y, then we can say it will always leave from the right, correct or not? From the left. And if my X is greater than Y, then I can say that it will always leave from the right. It will always leave from the right. And there the expression will look slightly different. So if it leaves from the left, then I can say that X only decides how many times it will hit the boundaries. If it leaves from the left, that means number of this is basically the deciding point. That many from these Y's is going to matter. Whatever is the number of Y can be greater than X. So we can say, okay, from 1 to X, we have to add all the Ri's. From 1 to X, we have to add all the Li's. That is how we will get for this particular case. For this particular case, X is less than equal to Y. For X is greater than Y, it will be slightly different. Why? Because now from the left, the last rebound will now push it to the right. So the only thing that matters is that last rebound. So you have got Y collisions. You move to the left for you can say Y collisions. For Y collisions, you can say, let's say this is the starting point. So for that, for the first collision, there was something in the right. Then for the second collision in the left, there was something in the right. And second collision in the left, there was something in the right, and so on. Now, when you come back, after Y collisions, all the right things are gone. After Y to and fro's, so when you have taken Y points from here, Y points already gone from here, and from here also Y points are gone. Which one has gone first? This one has gone first from the left. This one gets exhausted later. From there, when you come back, you have to hit the Y plus 1th point. Y plus 1th point. Which means from this point now, you will have the last free passage to the right. This is the free passage boundary. So you can say there can be other points as well before this, but they don't matter. So your X can be greater than Y, but this is what matters, only Y plus 1. So in this case, you will have a very similar expression. Just that the extra term will be instead of L3 to left, your calculation would go slightly different here. Instead of this, you will have few other statements. So you are at L3, or you are at, let's say, this Ly. Okay, from Ly you have to basically say, okay, go from Ly to R of Y plus 1. The way you are moving from L2 to R3, similarly Ly to R of Y plus 1. What am I discussing? Basically same thing. If the number of pointers is less on the right side, more on the left side, then this happens. And then this one will be basically the same kind of Ly minus R of Y plus 1. And from R of Y plus 1, it goes to the right end. So R of Y plus 1 to the right. This will basically be how many? Instead of L3 plus 1 what we saw there, it will be from the right end. Right end means, I'm sorry, right end means last element is n minus 1. Last element is n minus 1. So n minus 1 minus this plus 1, which means n minus r of y plus 1. Here also you see that r of y plus 1 occurs in pairs, and there was one ly over here, you have a similar ly over here. So the parity is not changing, they all still occur in pairs. So if you combine them, basically the expression that you get is somewhat like this, very similar to this. But slightly different. Here you have to say, okay, y is the deciding factor. To the lefts will be more engaged now. They'll be y plus 1. I'm sorry, the ones in the left that are pointing to the right, they will be present in y plus 1. And the li's are the same, they are present in y. And now instead of plus 1, you will have a plus n coming over here. A plus n coming over here. One extra minus term over here, or twice you can say, and plus n at the end. So this is how for different cases you can find. Now how many cases are there? We have found out 2 cases. There are 2 more cases. For both these cases I have actually done this, that this is left. Now if it moves to the right, I similarly have 2 other cases which are just symmetrical to these 2. So basically you will have these cases that your the starting position, so the direction at the start can be left or right, and then the x and y. X means the ones in the left and y means the ones in the right, their relationship. So you will see these relationships. One is, if it is going to the left, we saw this, that either x less than equal to y is one interesting thing for me. Other interesting thing is x greater than y. We have solved those things. So we have got those expressions. This is expression 1. This is expression 2. I can say these are my expressions, expression 1 and expression 2. Now if I go to the right, if I decide to go to the right, I'll similarly have 2 other cases. One is the one I'm hitting, that is the right. That is again less than equal to the opposite side. So it will be, in some ways, I mean, you will find some match with this and some other match with this. And this one will be y greater than x. These 2 expressions, you can, I would encourage you to find out yourself. It will look something like this. Since I have it noted because I had solved this, so let me write down Ri from 1 to y plus summation Li from 1 to y plus n, yeah, and the last one will look like minus p minus 2 of summation Ri 1 to y plus 2 summation Li 1 to y plus 1 plus 1. Right. These are you can check. Basically it's based on the same ideas that the previous ones are based. When it is greater, it will take an extra stab at the right before leaving the left. So that's the extra stab at the right. That's it. So you can check my code. Definitely my code is tested and I have created the code based on this, but if there are any differences you can find from my code. Now the next point is how to calculate this. Yeah, it is possible to maintain a prefix sum. See, what matters to me is up to a certain point water may arise. So I basically want to know, okay, summation of arise for all arise, or not all arise, let's say for some given number, some x or y number, some x or y arise just before start index, just before starting index. The nearest ones, let's say, matters to me. So I want to find out a particular, the summation of few RIs, maybe all, may not be all. I need to find out the summation of those RIs or the summation of LIs, summation of RIs before start index or summation of LIs just after the start index. How can we find it? Prefix sum is one very good option. So using prefix sum, I can contain the summation of right pointing arrows from the left and the left pointing arrows as well, and then I can target a range. So basically for any given start position I can say, hey, at this start position, for this start position I'll calculate the x and y. I will do this calculation over here. I will say, okay, what is required. Let's say I end up over here. It tells me that I need y number of LIs. To my right, I need y number of LIs. Y LIs. Now, what this means is y LIs are expected. Y LIs are expected. X is y is less than equal to x. I expect the y LIs over there. So I can say, okay, in the prefix sum, basically, I have to find out that in that array, which location is the first location after my start index. Let's say this is that location which is the first LI after my start index. So start plus 1, start plus 2, whatever. Not all of the places have left pointers. Let's say this is the first one. So what I'm interested is in from this j up to j plus y minus 1. So I'm looking for the summation of this. I'm looking for the summation of Ri values. So sum of Ri values from j to j plus y minus 1. What is this array storing? This array is storing Ri values for all positions containing Ri. Li values for all summation of Li values. So Li values for all positions containing right pointer. Right? In LIs we are considering right pointer. Is it, or have I just messed it up? No, LIs is left pointers. So yeah, to the right. Basically to the right I'm looking for the left pointers here. Left pointers. So now this summation, so what am I requiring here? First of all, to find this point, in order to find, okay, what is the smallest j? To find the smallest j for which the Ri is greater than start, for which Ri, the R value or L value, whatever, that L value, or let's say if this is this array of Li values, so let's name this as capital L, for which capital L of j is basically greater than start. How can we find this smallest j for which L of j is greater than start? Traditional binary search. Using binary search we can easily find out, or using 2 pointers. If we want to move from one index to the next index, this information can be carried forward, or using 2 pointers you can easily do this. Okay, next thing is, okay, you have found out the first point. Now the sum of those elements. you have to include y points. So the range is clear. When you have the range, the best technique, one of the best techniques definitely is the prefix sum. Whenever the range is clear, prefix sum will help you out. So L, let's say, contains the Li values. Then you can compute a prefix sum of this L array, which will look something like PL, prefix sum of L, and then from there target that range and find out something like this. So this answer minus this, I mean prefix sum up to here minus prefix sum up to here gives you the answer. So it will be prefix sum PL of j plus y minus 1 minus PL of j minus 1. I solved it today, but uh, due to code repetitions, etc., I faced some wrong answers and runtime errors. But then there is something I want to show you. This is how I basically made my approach or made my implementation far more decent, by which debugging or avoiding errors became far more easier for me. So see what I did. Over here, yeah, I created two functions saying that sum left up to. That means if I'm going to the left up to index I, uh, so index I is the rightmost index that I'll take in that range. So if I go to the towards the left, I want to take count number of CNT number of values, and the rightmost value will be rightmost index will be I. So give me that number, give me that summation. It will I've created this function. Why? Because I need this function at multiple different places, at 4 different places. So everywhere if I do these kind of things, that okay, if it is equal to this, if it is equal to that, it becomes a very clumsy code. And you can see I got 3 wrong answer or runtime errors due to the clumsiness caused by the code. Some right from, similarly I'm doing the same thing. So I'm focusing on the right. I'm basically saying, hey, count number of elements starting from I. So I am subtracting I minus 1, that particular prefix sum, and if I equal to 0, then I'm taking 0. Here I'm very frank that hey, this is the only corner case, I equal to 0, not I less than equal to 0. Then I'm very firm about it, that okay, if any other runtime error happens, let it happen. Then what? That will tell me some bug in my code, other part of the code. But now pref.get, this is the I plus count minus 1. So these two functions I've created, that made my job pretty easy. I came down. These are where I'm taking the indexes of the left and right pointers, my left array and my right array. Now there is a prefix left of this left array and prefix right of this right array. Whatever I was showing like PL and PR, these are the prefix things. Yeah, these are those arrays. Now for every position, this is what I'm doing. I'm doing a binary search. You can do 2 pointers also. I'm doing a binary search to find out these two things. What is the number of right arrows to the left of I? Number of right arrows to the left of I, and this is actually the last position of right arrow to the left of I. Similarly, I found out Y. Number of left arrows to the right of I and the first position of left arrow to the right of I. And then what am I doing? I'm basically saying, okay, if your current position is left, then there are 2 cases. One case is x less than equal to y, another case is x greater than y. I have created a third case saying that okay, if x is 0, then this is how you'll handle. X is 0 means you're going to the left, so it's a free passage. Just get out. You can avoid it actually. I think these things made things pretty difficult for me. And somehow I faced some issues, so I created this. But you can see, this was what I was basically computing. And I was computing this for 4 different cases. You can see how big this is, how many conditions are there. Where was that mistake, where I was hitting the wrong answer or runtime error was becoming very tedious for me. And that was when I said, okay, I should use something more decent. And I came up with this, okay, sum left up to and sum right from. Can you see? I'm just using the formula I minus 2 into sum left plus 2 into sum right plus 1 or plus n, whatever. Here plus 1 and here plus n. I'm just putting the right values and I'm done. So here, this is one example how modularity basically makes the code far more decent than this crap we had and made my life so easier. I was getting so many wrong answer verdicts and now it gave me correct answer verdict. So this is the benefit of good coding conventions. Um, Modularity, good patterns, etc. Now, this is for less, and for the greater ones, you can see the conditions here. Minus I, minus all those things. I had written them over there. You can tally with this. This one is a working code. This worked for me. So yeah, nothing different. We just used that formula. So what's the summary? Basically, I noticed that I basically expanded this form, and then adding things, I noticed that it's the summation of Ri's and summation of Li's that is giving me the answer. That's it. I proceeded back and I did the same thing. And I actually thought, had I done this in the contest, it would have been a great thing. But anyway, bad days come. Okay, so that's it, using binary search or two pointers and prefix sum and some good observations and some mathematical nuances. This problem D, could be solved. This was a pretty good contest in the sense that really tricky steps had to be adopted to solve many of these problems. So if you have not solved this problem, please solve this problem. This will also help you get some implementation practice. Okay. Now the next part is problem E. The last problem that we will discuss as a part of this playlist. So this problem is quite interesting because it deliberately made it confusing and multi-layered. So you are basically in some arena, and you want to have the nth Pokemon stand in the arena. Initially, the first Pokemon is standing in the arena, and now the ith Pokemon, or let's say something is given. Yeah, the ith Pokemon can win over the jth Pokemon. So ith Pokemon can win over, let's say, the current Pokemon based on some jth attribute. So ith Pokemon will win if that attribute is greater for ith Pokemon compared to the jth attribute of the current Pokemon. So it's something like this. If I give an example, let's say Pokemon 1 currently is there. Now Pokemon 2 can win, can defeat this and come over here. If it defeats this, it basically comes over here. But for that, the requirement is that some attribute has to be greater than P1. P1's attribute. So there has to be some J such that P2J is greater than equal. I think P1J. Let me check. Greater than or equal to, yes. So any particular attribute has to be greater. Then P2 can come. Then there has to be some P3 who will say, okay, for me, if some J dash is greater than equal to P3 P2 J dash, then this can come over here. This can replace P2 and come over here. So one Pokemon coming means other Pokemon going away. The current Pokemon going away. Ultimately, you have to bring Pn. You don't have to bring all of them. You have to bring Pn. For that, do you want to bring all of them or not is up to you. What do you have to optimize? So, cost of this operation is Ci. What is this cost? So if P3 is going to come, if you are going to use P3, this is going to be C3. This is the cost. If you want to bring P2, the cost is going to be C2. So that is the Ci thing. So if Pi is brought into is basically going to replace the current P, then this is going to be Ci cost. This is the cost. There is another cost associated, which is that you can increase the Aij by any k. That is, you can choose a certain Pokemon and increase their power or whatever. You can choose one attribute and increase the value of that attribute for that Pokemon by any number. Remember, if you are increasing that, definitely you are adding a burden for some other Pokemon as well, which cannot beat this or something like that. So that is one thing you have to keep in mind. The cost of this operation is k. So that means you can take any Pokemon. This is another thing. You can take any Pokemon and you can say, okay, you have to pick up the J and you have to say, okay, Pij plus equals to k. This is a permanent change. Okay, so for this, the cost will be k. And now, okay, I was writing there. Yes. So this thing for Pij plus equals to k, you have to select some ij and k, and then you can increase it. This is a permanent thing, and then the cost for this operation will be k. Now with minimum cost, you have to launch this Pn into that stand. With the minimum cost, you have to launch this Pn. Now, how to solve this problem? It became a lot complex due to so many conditions together. We can go through one example. Maybe you can read the notes for this. But yeah, so if I take one example, let's say 299617121, 299617121, right? 617121. These are for the three Pokemons P1, P2, P3, and their costs. Their costs for launching them are 231. 231. Now, if I want to bring P2, initially P1 is there, that is given, so I will have P1. If I want to bring P2, I can say that this attribute is greater than, it has greater value. So definitely P2 can come anytime. It can beat this and it can come at any time. And then what is the cost for going from P1 to P2? This is my cost. Because I'm launching P2, so the cost is 3. Okay, if I say let's directly try to bring P3, then what do we need? Either we increase this from 2 to 9 so that P3 can take over P1, right? So if I increase this to 9, then my k is equal to 7, already cost of 7. Big cost. If I try to take this to 9, the cost is 8. The k is 8, big cost. If I try to take this to 2, from 1 to 2, then this is a pretty low cost thing. K equals to 1. Only in one cost I am able to make a difference. I'll say okay, now once this has become 2, after you take this, now this P of 3 with attribute 1 becomes 2. From 1 it becomes 2. And then what can you say? Okay, now it is equal to this, now I can take over it. So now P3 can take directly over P1 using what cost? Using this cost, C3, it is 1. So one cost over here, one cost over here, plus one cost over here gives us 1 plus 1. Cost equals to 1 plus 1 is equal to 2. Okay. So in this way, we got the answer 2 over here. So you can understand there are so many cases possible. So how to solve this problem? This is a slightly hard problem because many conditions have actually come up and occupied the space. But the crux of everything is that you have to make some good observations and then rule out. You have to rule out possibilities. One possibility is that, okay, if I'm basically starting at one place, by the way, what kind of problem does this really resemble? This resembles one problem, that is, okay, what is the shortest, what is the minimum cost to reach from 1 to 3 or 1 to n? What is that minimum cost to reach from 1 to n given these different ways? There is one problem that comes to mind. Don't be afraid of mentioning that. That is going to be shortest path. The cost, the minimum cost to reach from one point to another, abiding by some path, some subset of paths, etc., is basically the shortest path algorithm, shortest path problem. Now, for shortest path, here, what is my source? The source is P1. What is my destination? The destination is Pn. For single source, single destination, we have a ready-made algorithm, very popular algorithm known as Dijkstra. Can we apply the Dijkstra directly? Now the problem is that those values are changing. Applicability of edges will change if my values are changing. But for that, we can actually make some observations. Let us see. So let's say From P1 we are going to P2, let's say. Next we are going to P3. Next we are going to P4, let's say. Let's say this is how we are going. Now for P1 I had to increase this, let's say Aij. I had to increase that Aij uh, by 5, something like that. Let's say by some value, plus 5. Then accordingly I have to, if I abide by the same attribute, then I have to increase this one as well. Let's say initially for a certain attribute j, the values were 2, 3 and sorry 2, let's say 10, 8 and 6, or let's say 5. Yeah, so this one I have to increase by 2 so that we could come to P2 using this attribute. Now for P3 this plus 2 forces it to increase by 2 more. It could have increased from just 5 to 8, but now it has to keep the 10 in mind, and it has to say, okay, initially if I create the path, I will say, okay, going from here to here involves a cost of 3 plus that cost of C3, right? This 3 plus C3, we can say, correct? But now this is an extra complexity that if it changes, then will I keep on changing the edges every now and then? If some edge basically is, I'm increasing some value of some node, for that will all my edges change? For this plus 2, earlier you were just doing plus 3 for going from this 5 to 8. You are just doing plus 3 so that this becomes 8 and then you can go directly. But now you have to do extra plus 2. And then your total cost becomes something like plus 2 plus 3 plus 2. To go from P1 to P3 you are bearing a cost of plus 2 plus 5, which is plus 7. But now if you observe a little bit, you will see, okay, if I go directly to P3, I don't have to bear this plus 2. That will just look at my 10, that will increase itself accordingly from 5 to 10, I am done. It will just take that plus 10, plus 5. So in plus 5, in total plus 5, here we are taking plus 2 plus 5, which means plus 7. But there in only plus 5, our total task will be done. So this one will be better, not this route. In other words, if this is telling you that the difference from here to here is 5, the internal fluctuations will not matter. Because if the internal fluctuations make things worse, you can always skip them. So I get one idea that, okay, sticking to an attribute, in an attribute, if some, let me take it that way, using an attribute P1 to P2 to P3 to P4 doesn't make sense. Using an attribute, I can say, okay, from P1 to go to a certain P4, let's say, directly, using a certain J. Then you should ideally use a different J dash to go to a different P7, let's say, J dash. There is no sense using the same J. There is absolutely no sense using the same J. Interesting thing now arises, okay, you can ask that, hey, now if I come to some P18 and now before entering into Pn, let's say I want to use J. Let's say you want to use J. So this is one J, this is another J. Now the question is that will this situation arrive or not? That I have J optimal over here as well as J optimal over here. Or shall we have a better way given this kind of a possibility? Maybe we can have. We can have this kind of a possibility. But now the question is, can we have P4 over here instead of P18? Can we have P4 over here, which we already have seen through J? That we cannot have. So let's say we are basically saying, okay, we'll first go to P4 and then we will go to P7 and then later again P4 and then to Pn. This will not happen because then I will say, okay, then this part is not needed at all up to here. From here directly you can go to Pn, correct? So P4 will not reappear. P4 will not reappear. In fact, P4 should not reappear in any different form. Forget J. If you have any J dash also, this should not reappear, because then we can do the same thing. We can eliminate this. We can say instead of this J dash, take the J double dash directly and go to Pn. So it should not reappear. That is the first thing. Same J's, we can say that J might reappear. At least at this point of time, I don't have sufficient evidence to say that J cannot reappear. So okay, that is not a problem. But what we have understood till now is that successively my J's are going to change, as a result of which um, these fluctuations don't worry me. More important thing is that a certain P will not reappear. This is a very big thing. Think through it, and please ask doubts on any channels, etc. If you feel you find some good insights over here. But this P4 is not going to appear over here due to this basic reason that then we will have a better answer through this path. So the thing is, if no node appears, if no node reappears, if no node reappears, and if J changes at every step, these two conditions are very important conditions for this problem. If no node reappears in the shortest path, and second is no two consecutive edges in the path use the same J, which automatically means that a certain node Px will have some J coming and some other J going there, which means that for one J, whatever change I do doesn't affect the other J. So Aij need not be remembered. Need not be remembered. This is an excellent finding which will help us solve the remaining questions so easily. This question is basically about making these observations and finally reducing it to an easy Dijkstra implementation. Aij need not be remembered. So now we can say that we can try to solve it now. Now one thing, how will the shortest path things now look like? How many nodes will I have? Basically, I can say that for this J kind of thing, I need to have separate nodes. Why so? Because you can say for the fluctuations, one way to basically look at this is that you have some P11 node, which basically means Pokemon 1 having attribute 1, and then that basically allows us access to Pokemon 2 with attribute 1. It can be 0 if this value is already greater than 2 1, right? If A of 1 1 is already greater than or equal to 2 1, then this can be 0. Otherwise, this can be the difference. So this is one way we can actually frame the edges, and we can say there will be some common connection with the P1s. If we found basically with all the P1s, P1, P2 in that way, if I basically say, okay, this is P1, this is P2, this is P3, what is the problem? I have so many edges based on so many attributes. I have so many edges based on so many attributes. With each of them. So if I think about the scale, let's just think about this. If I have so many edges and between each of them from there also I have so many coming here. So how many edges are there? Between any two, between P1 and P2, there are m number of edges, the number of attributes, that many edges. So total number of edges is going to be n square into m, roughly n square into m. What will that reach to? Let us see. N into m goes up to 4 into 10 to the power 5, and n alone can go up to 4 into 10 to the power 5. So basically around this is so you can say n into nm. So nm can go around 10 to the power 5, n itself can go around 10 to the power 5 roughly. So this product can reach 10 to the power 10 and even bigger. Very hard to handle. Storage itself is difficult and infeasible. We can't go ahead with this. So this was the starting point. I first thought that okay, we will have n different nodes and we will have these edges. Fluctuation doesn't matter, made things easy. But now we have to optimize. We have to remove unnecessary nodes, unnecessary edges. We have to remove unnecessary edges. Maybe that is one possibility. So this brings one idea. You can think in this way that over here, if we think in this way, we have this 10 to 8 to 5, etc. If we just have this one direction, do we need these extra paths? Do we need these extra paths? We don't need. If these are in the descending order of these aij values, let's say over here also we have something like 1. So if already these are in the descending order, I can say, okay, if I want to jump from here to here, this distance is what matters to me, 10 minus 1. So instead of 10 minus 1, I can also treat it like 10 minus 8 plus 8 minus 5 plus 5 minus 1. I can treat it like that. So fine, if I keep it in that way, that is one side of it, which means attribute wise, I can have only n minus 1 edges instead of n square edges, right? Between all of these, between 4, there can be 4c2 edges. But if we just maintain one line in this way, with these in the descending order, it becomes pretty simpler. It becomes pretty, simpler as in much less space overhead, and we can do the same things as we did before. So moving ahead now, total number of edges. Yeah, I'll think of a structure like this, that we have this P1. Let me see, I think I drew this somewhere that will make it easy for you. Yeah. So let's say we have this P1 and we will have P11, P21, P31. Similarly, I'll have P12, P22, P32. Similarly, I'll have P13, P23, P33, P2, P3. What is my P1, P2, P3? Those Pokemons. So P11 is basically when I choose that, okay, I will choose this first attribute for Pokemon 1. So I will have, so these three are basically Pokemon 1 with first attribute, Pokemon 2 with first attribute, Pokemon 3 with first attribute. This is something I'll have. So I'll say, okay, if you choose to use the first attribute, if you choose to use the first attribute, We can definitely go there. We can definitely go there. We can definitely go there. These are, I mean, we can choose any of these attributes for P1. Now, my way will be that, okay, from there, I will now try to find out the shortest path to this P3. So the strategy would be something like this, that I'll try to go there, maybe from here to here, and from here I'll come back over here. At this point of entering P3, I will impose that cost of C3. So the cost of C3 will be here. From P3 to also, if I want to enter P3, we'll have the cost of C3. From here also, if I want to enter P3, I'll have the cost of C3. So first time launching a certain leader will take this cost. And we have seen we will not launch two leaders, I mean the same leader twice. We have already seen that. So whenever we want to come over here, we will use C3. This logic holds. If I want to go the other way, which I have done using those pink arrows, if I want to go the other way, there I should not need any cost, because I'm basically going and saying, okay, please use your weapon, please use your third weapon, what is that called, third attribute. Yeah, third attribute. Here I'll say again third attribute. For that there is no cost, so I will mention the cost as 0. For this there is no cost, but there are edges, you can go anytime you want. This also gives me a passage that, okay, I come here through C3, then I can go using this particular attribute, go anywhere else. We can do this. Okay. If I complete the diagram, basically from here, coming over here, this is not needed, but this will be C1. Similarly, this one will be C1. This one will be C1. Similarly, over here, these will be 0, 0, 0. And coming to P2 will cost C2, C2, C2. Okay, what next? Next thing is, across these, how will I move? From the P1 block to the P2 blocks or P3 blocks, how will I move? P1, P2, P3. Let's take that example. P1, P2, P3, these are my examples. Let us take these examples. So, using attribute 1, if I want to move from P1 to P3, if I want to move from P1 to P3, then that is not free for me. I need an escalation. I need a cost of 1. I need to increase this by 1. If I want to move from 1 to 3, I need to increase this by 1. Which means if I want to move from here to here, that involves a cost of A31 minus P31. Sorry, A11 minus A31. A11 minus A31. If I want to come back, that is also possible. If I want to come back, basically I need a cost of 0. Now how did we choose to order this? We said let's not form between all the pairs. Let's order it. So in what order do you see this? For this particular attribute, it is in this order: P3, 1, P1, 2, and P2, 6. So we will only have these two and these two. Going forward from P3 to P2 and coming backward from P2 to P3, we will not have between P3 and P2. Okay, so between P1 and P2 we will have this. So going forward from P1 to P2, going forward from P1 to P2 will not cost me, because I am having a bigger party there. So this will be 0. And coming back from P2 to P1, P21 to P11 will be A21 minus A11, which is 6 minus 2. This will be A21 minus A11. All these subtractions, these differences will be positive. Okay. So over there, if you want to see what are those values in according to the question, this value will come out to be 1. This value will come out to be 1. So you will come through 0 over here, then you will come through 1 over here, and then you will come through 1 over here. In this way, you can reach P3. Ultimate objective is reaching Pn. Right? So in this way, you can fill up all of these. Similarly, you will fill up these. This one, and this one will be connected. Right? This one, and this one will be connected. So, yeah, these three. And these three will be connected. Yeah. So as an example, you have 1 to 1 over here. So definitely, this is what I should be looking at. 971. So from 1 to 9 or 1 to 7, anytime you can go. We will go from 1 to 7 and 7 to 9 in 0 steps, basically. So P3 to P2. P3 to P2 you can go in at 0 cost, because at 2 the attribute has greater value, and this also at 0 cost, and you can come back from P1 to P2. You can come at cost 9 minus 7, that is 2, and from here you can come back at cost 7 minus 1, that is 6. So this is how we can complete the graph, and you just have to start from this index and reach this index. Over here, this is your source, this is your destination. So what is the shortest distance? You just have to apply basic Dijkstra over here. So Dijkstra in the above graph gives you the answer. Dijkstra on above graph gives the answer. What is the cost of building the above graph? What is the number of edges over here? That is, I think, the biggest thing that we wanted to improve. So number of edges basically is between Pi and Pij, all those Pij, we will have 2 into m into n edges plus, these are between the Pi and Pijs among them, and then between different Pijs, that is these ones, how much will have? What I mentioned was for only these ones. This plus this is 2m into n, and now we have among these, which will be n minus 1 multiplied by 2 multiplied by n. So n minus 1 multiplied by 2 multiplied by n. So the overall thing comes to 2, or we can say 4n minus 2 into m. N into m is given, that will not be above something into 10 to the power 5. So the overall thing stays within 10 to the power 6, or maybe 2 into 10 to the power 6, something like that. That is the number of edges. In Dijkstra basically works with big O number of edges plus number of vertices. So if it is linear in number of edges and number of vertices, we are good to go. Oh, okay, sorry, it's not so exactly. It's actually into log in number of edges multiplied by log number of vertices. Anyway, for this I think 3 seconds are given, so slightly greater time is expected over here. 3 seconds. I think my submission took around close to 2 seconds to execute. So I hope I could make the the intuition clear why we did it in this way, and then I hope the basic approach etc is clear, how things are working and how the solution is obtained for at least one test case you could figure out from here. Please try out this for some test cases and please try to implement it. I'll show my implementation. Please try to implement it because that will help you basically uh, able to solve similar problems going forward. So we have, I'm taking the inputs over here, lot of sorting it. Here I'm basically sorting that, okay, based on each attribute I'm sorting them. So pj means all the aij's for a particular j. So for a particular j I'm basically putting them in pji, something like this, and then I'm taking that pj, and then what am I doing? I'm saying that, okay, these are those first set of edges, these edges, these edges I'm first forming over here, and they have the cost of CIs, and these are the other set. These are these sets. So there I'm basically saying go in that line of sorted order. We are sorted in this P, right? In this P we are sorted. So now I'm going along that P. So along that P I'm going. It slightly looks difficult, but I'm basically converting them to integers so that I and j now give me a single number. So I'm basically converting. So it became a bit complicated, and I had to also put some print lines to debug it. But yeah, then you can use your tree map, tree set, all those things in Java. I've used priority queue. There's slightly redundancy in priority queue. That's also a reason behind the time. But yeah, then what am I doing? I'm doing simple Dijkstra. This is the Dijkstra code. So please study the Dijkstra code. Later on, maybe sometime I'll attach some video describing how Dijkstra is done. But for now, you can read Dijkstra from CP Algorithms website. Um, it's not in algorithm, I think it should be in Dijkstra, yeah, Dijkstra algorithm. You can read from here. Yeah, I showed one other solution, one tourist solution I remember, where a linear Diophantine equation was also involved, and I showed using, where how he had used Dijkstra as well over there. So you can refer to that. You can see how these similar problems work. Simple Dijkstra you won't get in these good problems. You will get all these variations, but ultimately they will end up in a simple Dijkstra. At least these E kind of problems. So over here you see I was fetching the best till now, and then these are sanity checks, and then I'm fetching their neighbors. If any neighbor sort of gives me a new better cost, I will add that into my priority queue or whatever data structure you're using, red, black, tree or whatever. And then finally this is what I print, answer of n minus 1 into m minus 1. So that's how I'm basically doing this. And so for a of you can say for the xth Pokemon yth attribute, I'm basically storing it as x into m plus 1 plus y. Y ranges from 1 to m. So y equal to 0 denotes the normal P1, P2 nodes that I am mentioning over here. P1, P2, these are the actual P1, P2 nodes, and those are the attribute specific nodes. So for attribute specific, I'm using these y values from 1 to n, and for those which are not having any attributes, which are my final source and destination, and also my intermediary points. Why intermediary points? Because if I'm using one attribute, let's say I'm using attribute 1, and I'm, let's say, going over here, and then in order to use another attribute, I have to come and take this P2 and go use another attribute, and then using that I have to take some other stance. So since I have to change attributes, so visiting this P2 becomes essential, and when I'm visiting this P2, I am automatically incorporating this C2 addition. We will not be visiting P1 again, so this won't come. So yeah, that's it. Now where were I? So this is how I'm basically taking this in one integer so that I don't have to maintain too many pairs and everything. This is one integer, that's what I'm storing. You can store it as pair as well if you find that implementation easier. And then that is what I'm displaying. So n minus 1 into m minus 1 basically means n minus 1th Pokemon with no attributes. N minus 1th Pokemon, n minus 1 into m plus 1 plus nothing. I mentioned here plus y. So since y is 0, that means I'm referring to the actual Pokemon with no attributes. So that means it will consider that Cn, definitely. So yeah, that's it. I hope you got to learn something from about intuitions of solving these problems from these videos. So let me know if you have any doubts, etc. Let me know if you liked this video, and do share with folks who you feel might find this informative. You can see a good deal of effort actually went behind this, so you have no idea how much your likes and shares will actually mean to me. They'll mean a lot to me. Again, thank you for watching it through. Take care, keep coding, and see you all in the upcoming videos, solving and upgrading your problem solving skills. So yeah, that's all for the day. Take care, keep coding. See you in my next videos.